proceed further, there is another important concept which needs to be addressed with respect to rotation about a fixed axis, that is namely the angular momentum. So we will have this angular momentum, today's topic, in the case of rotation about a fixed axis. So what are the various things we propose to study today? We will first arrive at an expression for the orbital angular momentum. This is for a symmetric body rotating about a fixed axis. Then we will see that how the principle of conservation of angular momentum looks like, and we will consider a couple of examples. Then third thing is rotation, rolling and slipping. These are the various kinds of motions possible for rigid body. We will focus our attention on rotation and rolling. For slipping, maybe we will spend a time later and we will consider an example. This is what we propose to do. So I have here a diagram. When a rigid body is rotating, this kind of diagram we have seen, and this is the center, this is the radius vector, this is with reference to a suitable origin O, this is the point P, the OP vector is what we call it as the position vector R, okay, and the particle is going around like this, so I can indicate it by this arrow. This is the z-axis. I have x-axis here, x, y, z here. Okay, so omega is the angular velocity, let me say, and then m is the mass of the particle, and then here we have, let us say, two things. One is the linear velocity v, m is the mass of the particle, linear velocity, okay, and angular velocity vector also I need to indicate. Remember, this vector is tangential to the circle, so it is not vertically upwards, even though it looks like this in the diagram. Now the body is rotating, no, therefore it has got an angular velocity omega, and I need to draw a vector here which is the omega vector, and these two vectors are actually parallel, we will see, which is not clear here in the diagram. So we study the angular momentum in the special case of rotation about a fixed axis. So what is the general expression? The general expression is ETL for a single particle is R crossed with P. R crossed with P. So I have R is equal to OP. In this case, R is equal to OP vector. That is equal to OP vector is OC plus CP. OC plus CP, and where the P is equal to, the momentum is what? This is momentum vector is m times the velocity vector, linear velocity. These things are fairly standard. Okay, now I will calculate L. Angular momentum vector is R is OC plus CP cross this with m times V. I need to show the cross, sorry. This is equal to OC crossed with m times V plus Cp crossed with m times V. Remember, the cross product is distributive. And now Cp has got a name. This is what is called as R perpendicular. This we had seen it in earlier lecture. So V will be, value of V would be, velocity, linear velocity would here would be R perpendicular times omega. Therefore, I can write now L is equal to OC crossed with M omega, MV, sorry, plus CP is R perpendicular squared, then I have M, then omega. What is the direction? That is the K direction, unit vector K along this. So I have here, this is equal to, I will write this as, this is the expression for Z component of angular momentum. So I will write this L as L sub Z plus OC times MV. Now LZ is parallel to the fixed axis. Now this direction of this direction K can be obtained from this right hand rule also. That's how we can get it for that matter. Now what we have is LZ parallel, LZ is parallel to the fixed axis K. But you can't say that L itself is parallel to the this K, unit vector K, sorry, Z axis. I can't say that this is parallel to unit vector K. This is not correct. This is right. This is wrong. Okay. In general, the orbital angular momentum is not along the axis of rotation. L and omega need not be parallel in general. In general, L and omega need not be parallel. But in the case of an object rotating about a z-axis, that too for symmetric bodies, L and omega are parallel. Now we will calculate what is total angular momentum. This whole body is made up of so many masses. Therefore, total angular momentum is sum of all the angular momenta, because angular momenta is a vector quantity. The summation runs over I corresponding to all particles. So this is Liz is Z components of all particles plus sum over OCI crossed with M times VI. It is straightforward generalization. Now we call this quantity L as L is Z. This is the cumulative sum of all the Z components, this term, plus the other term is L perpendicular. This is the term. So L perpendicular is the other quantity, which is encircled. So what is, let me write this Liz vector. Liz is equal to summation over Liz. This is equal to sum over all mi or perpendicular I squared times omega k. Omega is the same for all at mass at every point, therefore omega can be taken out. So Liz is equal to, what is this quantity? This is the moment of inertia. This is the moment of inertia of the body about this particular axis of rotation. this is the R perpendicular. Let me indicate here. This is the R perpendicular. At this particular point, there is a mass mi, and its perpendicular distance from here, and the distance from C is R perpendicular I. Therefore, this is the I omega times k. So this equation is something, reminds us a bell should ring in our mind. It is something similar to, I will write it as P is equal to mv. P is equal to mv in the case of linear motion. So in the case of symmetric rigid bodies, what happens is, for a symmetric rigid body, for every OCI, for a given OCI, for every particle which has a velocity vi, there is another particle with a velocity minus vi. If it is a symmetric body, given this OC, if there is going to be a velocity in this direction, there is going to be another particle which is diametrically opposite at the same distance with a velocity minus vi. Therefore, these two components will cancel, so you are left with that L perpendicular is equal to 0. So hence we have, for a symmetric rigid body rotating about a symmetry axis, Lz is equal to I omega times k. So the axis of rotation is also same as the direction of omega. Now for objects which are not symmetric about the axis of rotation, L is not equal to Lz, that you must keep in mind, and hence does not lie along the axis of rotation in such cases. We will consider a few illustrations. Example 1. Let us say that I have a circular disc. It is a circular disc. This is the axis of rotation. This is axis of rotation. This is z omega, and its radius is r. Now I want to write down what is the angular momentum vector. Angular momentum vector is equal to, this is symmetric body. This is the axis is also symmetry axis. So therefore L is nothing but I omega times k. Fine. Now what is the moment of inertia of a circular disc? Yesterday we had seen mr squared by 2, and angular velocity is omega, this times unit vector which is along the z direction. Now I can do a slightly different problem. Example 1 here. This is example 2. What I will do is, in the earlier problem, what I have done is we have coincided the z-axis with the symmetry axis of the body. In fact, suppose the z-axis lies outside, and we have the same situation, same body. Okay, everything is same. It is rotating with omega, and these two axes are parallel. Then again L will be equal to, now this symmetric rigid body rotating about the symmetry axis, therefore its angular momentum is given by I omega times k. But only thing is I is different. This I is the moment of inertia about the symmetry axis, that is mr squared by 2, but this is, we are calculating with respect to this, therefore we want to know the moment of inertia about the symmetry, about the z-axis, therefore this is md squared. This is what we call it as parallel axis theorem. This is the parallel axis theorem. This I will indicate it as parallel axis theorem. This times omega times k. That's the moment. So we have got the moment of inertia of this object. We will make few comments before we proceed further. So L is equal to I omega times k. Now what is dl by dt? dl by dt is equal to I into d omega by dt times k. This is equal to d omega by dt is alpha, therefore I alpha times k unit vector. I alpha yesterday we have seen is nothing but the torque. Okay. So now we calculate, since L is equal to Lz plus L perpendicular. So what do we get? dLz by dt is equal to tau times k, and dL perpendicular by dt is equal to 0. Now this gives rise to the principle of conservation of angular momentum. Principle of conservation of angular momentum. Now this is generally PCAM, some abbreviation. The total angular momentum of a system is constant if the resultant external torque acting on the system is 0. The total angular momentum of a system is constant. In other words, it is conserved if the resultant external torque acting on the system is 0. Now we are considering with respect to symmetric rigid bodies. Therefore, we have the angular momentum, initial angular momentum is same as final angular momentum times Wf is equal to constant. This is a sort of statement for the angular momentum conservation. Okay. Now this conservation of angular momentum is something similar to, it should again, a bell should ring, principle of conservation of linear momentum in the case of linear motion. Just for comparison purposes I am indicating it. We will do an illustration of this. We will do a problem or illustration. Now, say I have the situation is like this. I have a cylinder. This is the axis of the cylinder. This is the axis of the cylinder. Okay, this is the horizontal axis, axis of the cylinder. This is horizontal. This is horizontal. Now there is a mass, there is a bullet which comes and hits it. Actually, the way I have indicated, it looks like it is a normal. This comes M and V naught. Okay, so the bullet hits the direction of the bullet is perpendicular to the horizontal axis of it, meets at a particular distance. Let us say the distance between these two is D. The bullet hits the cylinder at a particular distance D from the axis. Okay, and R is the radius of the cylinder. So see, I need to say that this is the line of motion. The line of motion of the bullet. It is perpendicular to the axis of the cylinder. Even though in the figure it may not be like that. That's why I am writing this. Okay. Now we various things can be calculated. At least we can calculate the angular speed of the system after the projectile strikes and gets embedded on the cylinder. Initially the cylinder is at rest. After the bullet strikes the cylinder, the whole system will begin to rotate. We can calculate the angular speed of the entire system. So here we can apply the principle of conservation of angular momentum, because there are no external torques. And so before collision, before collision, only the bullet has the before collision only the bullet is moving. It has an angular momentum with respect to the axle. Before collision, only the bullet alone has the angular momentum with respect to the axis of the cylinder, and its value is momentum is angular momentum is L is equal to M into it V naught into D. Okay, M V naught is the momentum, that into the distance. Now it is directed. Okay, after that, after the collision, what is its angular momentum? Its angular momentum is I times omega. Total angular I times omega. What is the I? I is nothing but I of the solid cylinder plus I of the projectile, because the projectile got itself embedded onto the cylinder, and this times omega. Okay, Li, I will call it as Li, L final. Therefore, now we can equate these two. So I have mr squared by 2. Solid cylinder is mr squared by 2 is the moment of inertia, plus after it got embedded on the surface, the mass of the bullet is m, as we said it. It is as a distance of r. It got embedded on the surface. Mr square times omega. This is equal to initial angular momentum. Initial angular momentum is m into v naught into d, that corresponding to only that of the bullet. Therefore, this implies omega is equal to m v naught d divided by mr squared by 2 plus little mr squared. In fact, this expression can be made use of to find the velocities of a bullet, because the bullet will whiz past very fast. So once you make this bullet hit a cylinder, get it embedded on the surface, that is important. It has to get embedded on the surface. Then we can measure the omega. Through that we can measure the value of V naught. Okay, we will consider one more illustration, one more example. The situation is like this. I have a circular disc. Okay, this circular disc, it has got an axis, and it is pivoted. So the disc can rotate about this axis. It is pivoted. So this is, and the mass of the entire disc is m, and r is the radius. The center we will call it as C. Now, as it is rotating with a constant angular velocity omega, here we have a mass little m, and it begins to roll towards the center and reaches a particular point, let us say C, such that OC is equal to x. As it moves along, what we are the question is, there is a point C it has to cross. So we want you to calculate the so calculate omega. Question: what is this? Calculate omega when it is when the little mass reaches C. That is the thing. Initial value of angular velocity is omega. As this m is considerably heavy, it is not negligible compared to m. Therefore, as this mass moves towards O, the whole angular velocity will change. Now let us see what happens to it. So this is a circular platform. I will call it as CP, circular platform. Let me repeat the problem. There is a circular platform of mass m, of radius r, which is pivoted about a particular point O, which is rotating about an axis with angular velocity, constant angular velocity omega. A mass small m, it begins to move towards the center. Initially it is at the rim of this circular platform. You are required to calculate the angular velocity of the entire object when it reaches C. That is the question. Now, again there are no external torques, therefore the angular momentum, orbital angular momentum, initial is equal to orbital angular momentum later, angular momentum at later, at some instant of time. Now, first let us calculate what is the, we need to make use of the formula L is equal to I times omega, right? So we need to know what is the initial moment of inertia of the system. Initial moment of the system is I of Cp plus I of mass. This is equal to the circular disc, therefore mr square by 2. Cp is the circular platform plus little m into r square in the beginning. Now If is equal to, again the same thing, this is equal to m r squared by 2. But now the mass is at the point C, which is at a distance x, therefore m into x squared. Now I am going to make use of the principle of conservation of angular momentum, which says moment of inertia initial times omega sub I is equal to moment of inertia times later omega sub f, right? So we equate these two, and we can so mr squared by 2 plus mr squared into omega is equal to mr squared by 2 plus mx squared times omega at c. Therefore, omega at c, when it, omega at c means the angular velocity of entire system when the mass is at c, okay, is equal to mr square. Let me write this in a little neat way. Mr square by 2 plus little mr squared divided by mr square by 2 plus little mx squared times omega. Okay, now it is clear that omega c is equal to this, omega c is greater than omega. That is because look at this numerator and denominator. The denominator, you are having a smaller quantity x square here. Therefore, omega c is going to be greater than omega. What does it mean? It implies that the rotational kinetic energy at c is greater than rotational kinetic energy initially. That means as this mass little m moves towards the center, the kinetic energy of the entire system is increasing. How does this happen? It happens because now if this as the mass m moves towards O, in order to keep itself in a position, it should apply, there should be a centripetal force. It has to do work to create centripetal force. Therefore, energy is given to the system. The kinetic energy is some energy is given to the system. Therefore, the kinetic energy of the system increases. One can calculate what is the amount, what is the increase in kinetic energy. This can be calculated because the expression is half I. We know what is the kinetic energy initially, half I omega I squared. We are calculating what is omega c. Therefore, again we can calculate the kinetic energy, calculate the difference, and right. Actually, this work done as this body moves along is transferred to the internal energy of the system. Right. Now we will move on to the next topic. Next topic is rolling. We'll call it as rotation, rolling, and slipping. Now I will give a little bit of motivation for this. The motivation is like this. I have a table top, let us say. What I do is, I have a disk which is rotating about its axis with some angular momentum omega naught. I am having a disk which is rotating about its axis with angular momentum omega naught, and I place it gently. The disk is, the rotating disk is placed gently rotating disc is placed gently on the table. Let us say it's a perfectly frictionless table, right? Now I will consider this point as A, this point as B, this as, I will consider some point here which is C from the center. Okay. So let us say that OC is equal to R by 2. What is happening? What is the linear velocity at A? Linear velocity at A is R omega and radius is R, therefore R times omega naught. What is the linear velocity at B? Linear velocity at B is equal to R times omega naught. What is the linear velocity at C? Again, whatever is the radius is R by 2 and omega naught remains the same. Why are we giving this example, sir? It is just to show that because the table is frictionless and the disc is rotating with an angular velocity, if it is placed on it, it is placed on the rotating disc is vertically placed on the table very gently. Very gently means that no push or anything, slipping, no push or anything. Then what happens is that when you calculate the linear velocities at various points, these are the values. Okay. Now the question is, the disc will only rotate. Disc only rotates. Now the question is, will it roll? No, it will not roll. It will not roll. If you place a rotating disc vertically on a perfectly frictionless table, the disc will not roll. This is the point which I want to stress here. Okay, now we will consider rolling motion. What is actually a rolling motion? A rolling motion is a disc will rotate about an axis and also it will move forward. Something like when you cycle or any two-wheeler, the wheels will rotate about the axis and also the wheels will move forward. So there is a translational motion as well as rotational motion. Now I will draw the axis. This point I will call it as P1. This I will consider as P0. This is center, I will call it as C. Okay. Now the whole thing is rotating. Angular velocity is omega naught. So at this particular point, what is the linear velocity? Linear velocity is V1. Right. Here it will be in this direction. Now suppose I take any point here, let us say I will take a point here. First thing is, this will have a center of mass. This particular point will have a velocity VCM. At the center it will move because it is rolling as well as rotating. There is a translational motion. Therefore, the center of mass will have a velocity which I will call it as VCM. I am not writing the vector so that it will get cluttered, but otherwise it's a vector quantity, direction is indicated here. When I take a particular point here, what happens? Now to find the velocity here, I should join these two. Okay, this particular point will have a center of mass. This will have a same CM, right? And now what I should do is I should there is going to be a this I will call it as RP. Then this is how it will have. I will call it as, this quantity will be the linear velocity. This linear velocity at P. This is the linear velocity vector. So the net resultant is going to be, I need to compound these two, right? Which I am not indicating it over here. So if I want, I can do it here. This portion alone I amplify it here. This is VCM. I'm magnifying it rather, and then this is VP, linear velocity. So I can complete. This is what is going to be the actual velocity at this particular point. Okay, this is P. I am magnifying this portion alone here, right? At P naught, at VP naught, at P naught, at P naught, what will happen? Due to rotation, it is exactly same as VP naught. So VP naught at this particular point, its linear velocity must be same as P center of mass. In other words, when the center of mass motion is like this, here it will have motion, and then its linear velocity will be here. Both of them should be equal. This is what is equal to R omega naught. So there is no at this particular point P naught, when it is rolling, it should be at instantaneous rest. That is what you call it. P naught is at instantaneous rest. Why it is at instantaneous rest? That is because its linear velocity should match the velocity of the center of mass. Okay, so we call it as VCM, velocity of the center of mass should be same as R omega naught. If this happens, as long as this is maintained, this is the condition for rolling without slipping. Condition for rolling without slipping. Okay. Now, what about the instantaneous? What about at P1? P at P1 is equal to velocity of center of mass plus R omega. Therefore, this will be equal to 2 times V of Cm. This is again for rolling, right? Okay, it will have a center of mass velocity as well as the linear velocity, and then the linear velocity is same as R omega naught. Therefore, it is twice Vcm. Now we will derive an expression for the kinetic energy of a rolling motion. So, kinetic energy of rolling motion, K is equal to kinetic energy of a rolling body is, so remember, a rolling body has kinetic energy of translation plus kinetic energy of rotation. See, you people, students should clearly distinguish between rotation about an axis, the translation about an axis. Both put together is what is known as the rolling motion of a body, right? So earlier we had seen, now we want to recollect something. Therefore, I will draw in a different colored. Earlier we had seen a kinetic energy of a system of particles. I think it is in lecture 2, I guess. As soon as we introduced the center of mass, this we did. In fact, we did a two-body problem. So kinetic energy of a system of particles is equal to kinetic energy of the center of mass plus kinetic energy of rotational motion about the center of mass. That is important. This we had done. So in the same way, we have, so the kinetic energy is equal to of what we are rolling body is equal to, first, translational motion. If the mass is m, v cm squared plus the kinetic energy of the rotational motion about the center of mass. This is half I omega squared. Right? And moment of inertia is also written in terms of mk squared. Let me use little m, mk squared, where k is the radius of gyration. Okay, which we had seen earlier. Now k is equal to half mk squared v cm squared by r squared. Well, how do I write it? That is because P of center of mass is equal to r omega. Condition for rolling. So this plus translational motion, energy for the kinetic energy of translational motion, V of cm squared. Therefore, K is equal to half little m v cm squared 1 plus k squared by r squared. This is a very standard formula. Okay, this is a very standard formula in that. So what is that we have done? The kinetic energy of a rolling body. So we have made use of, what we have done is the Ke of a rolling body is equal to kinetic energy of translation plus kinetic energy of rotation. Okay, this is something similar to, this is nothing but what we already have done in the case of many particles. Both are actually the same. We have got an expression for the kinetic energy. Now we can make use of this expression. Time irka sir, no?
2 minutes.
2 minutes irka. Now we can make use of this expression to do a simple problem. It is like this. what we have is, I have an inclined plane. I have an inclined plane. I have an object. It may be sphere or a cylinder or circular disc. It begins to roll. It rolls down. So I have a ring and a solid cylinder and a sphere. Okay. Now at this point, this whatever it is, if it is let us say it is a ring or a solid cylinder or sphere, the object will have only potential energy. When it comes here, it will have only kinetic energy. Therefore, mgh is equal to, expression for kinetic energy is mv squared by 2, v is the center of mass, of course, 1 plus k squared by r squared. We have just derived it, right? Suppose it's a, now we will have a small table. Now it is object. So நம்ம பண்ணிடலாம், எடிட்டிங்ல பார்த்துக்கலாம்.
Okay, sir.
Even if it is little more. This object. First I will have a circular ring. What is its k value? Radius of gyration. It's a circular ring or a disc. It is only circular ring is r. So I will put this expression here and calculate what is v. I will get, from this implies v is equal to 2gh by 1 plus k squared by r squared square root. So this will be gh, because k is equal to r, so 2 and 2 will get cancelled. This is what we will have for a circular ring. In the case of a circular disc, this is this is r by root 2, therefore it will have 4 by 3. It has higher value than this. Next we have a sphere, solid sphere. It is root 2 by 5 r. Radius of gyration is root 2 by square root of 2 by 5 times r. Then it will be 10 by g gh. So you realize that even though all these objects, ring or a solid cylinder or sphere, have the same radius r, same, all of them, they have the same radius, you will find that the solid sphere, when it comes to the bottom, it will have the maximum, it will have the greatest velocity. Greatest velocity is for the solid sphere. Therefore, greatest kinetic energy.